Who's ready to join the reference group for this course? Very good. What is your name? Okay.
I can use yours.
Right, that's good. Thank you, Anne. Further people. We have many exchange students here. What is your name?
Nicola Stapin.
Nicola. Okay. You come also after the lecture. Very good. Nicola, Anne. Any more? Okay, very good. What is your name?
Anna.
Anna. Okay, very good. So then we have three. So I understand that Nicola and Anna, you are exchange students, is that right? Yeah. And which study program do you?
Energy and Environmental Engineering.
Okay, very good. Do we have anybody from PUP, Mechanical Engineering, ready to join?
I come from there.
What's your name? Eivik. Very good. Okay, so those Eivik, Nicola, Anna, and Anne, please come after the lecture and give me your email addresses, and then we decide on the first meeting. And the others, please, you can give me directly feedback, but you can also give feedback through the people in the reference group. So we have seen them now, Anne, Nicola, Anna, and Eivik. So you can address also your ideas to them, so that I get to know them. Very good. So then we proceed with the upwind method. We have seen now how it looks like and what are its properties, but we can also write the flux in a different way. We have seen in the beginning 8. We have to decide from which side the wind is blowing to decide then on the convective flux for the upwind method. But we can also write it in one formula, and that is the following. So that is the upwind flux, flux 8 can also be written as, that is the following, that I call 12, that we have the UT, that is the convective flux. Again, we focus on the phase J plus 1/2, so that is our eastern phase. And the claim is that this is equal to the average of the following. That is the this convective flux expression UT in the cell J plus UT in the cell J plus 1. Since U is constant, this is just U times the temperature in J plus U times the temperature in J plus 1. If we would stop here, we would have the central finite volume method. But we continue. We have here minus the absolute value of U, our advection velocity, times the difference in T. So that is now the claim that this is the same as what we had in the flux, in the upwind flux 8. It's just to test it and to check it. If U is positive, we can remove the absolute values from the U here. And in that case, you see that the UTJ plus 1 and the UTJ plus 1 cancel. They go away, but here we get minus, we get UTJ. So we get it twice. With this divided by 2, we get UTJ. And that is exactly what we said, what the flux should be if U is positive. Number 1. Number 2, if U is negative, then the absolute value of U is equal to minus U if U is smaller than 0. You can think of it. If U is negative, the absolute value is minus U. Because then the negative gets positive. So that means we can replace the minus absolute value then by minus U. It gets a plus U here. So instead of, so then we have a plus U times this difference. And then this guy and this guy vanishes. They vanish. And we get then plus u, tj plus 1 here, and here we get it twice. Divided by 2 is u tj plus 1. So we get exactly what we want. So that means these expressions, 8 and this expression 12, are equivalent.
Excuse me?
Yes?
Could you repeat once more why you can say that the absolute value of u is minus u?
Yes. Absolute value of u is if u is negative minus u. Take an example. We have minus 5. Right? Minus 5 is negative, and I claim that is that.
Oh.
So it's not
Okay.
more than that.
Yeah.
It's just a way to express then the value, and the absolute value then is then the negative of the number.
Yes.
So in that case, then we have this. So these are equivalent. The advantage with this is that we don't have an if statement. If statements might take time. Of course, then you have to interrupt the computation and to check whether u is positive or negative. If u is changing sign, in our case it is not. So in our case we have no need. But when we come to nonlinear problems, then there will be a need. Then it might change, and we have to check at every cell face from which side the wind is blowing. So then it can make sense to have this form instead of the form where we have take either the value from the left or from the right, depending whether the velocity is positive or negative. So we have this form. That is now we have then seen now that it is equivalent to to the form 8. And now we can identify here things. The first thing is that this part here, if we just stop at this part here, that is the central finite volume method. Because if this vanishes, we get exactly what we had in the beginning today. That is the central discretization here of the flux. Corresponding, if we would stop here, corresponding to the central finite volume method. The term here we can isolate a little bit, and if we look at this term with a half in front, then this second term looks like minus, I add the 1/2 here, absolute value of u times tj plus 1 minus tj. So that is corresponding to the second half. If we would have a bracket here, minus, and then we had 1/2 this. So this is what we have here. Now to make it understandable what this represents, we simply divide by delta x and multiply by delta x. So this is minus 1/2. And then we have said we multiply by delta x and we divide by delta x. So that is just, I've multiplied and divided. I have not changed anything. But now we see something that is familiar to us. Because this here is the discretization of the time derivative dt dx at the phase j plus 1/2 that we have seen for the heat equation. It's exactly the same thing. Now it's appearing here. Remember, we are on the left side of the equation. We have dt dx plus times delta x plus the fluxes right minus fluxes left. If we would move this to the right-hand side, this would get a plus sign. And this guy here plays the role that the thermal diffusivity played before for the heat equation. So we can identify this term here as numerical diffusivity. So we can say that the term absolute value of u times delta x half is numerical diffusivity. What we have considered in the heat equation, that was the thermal diffusivity. That this is a physical quantity, but this is purely numerical. And another name is also, it's also called numerical viscosity when it comes to problems involving the momentum equation. So that is more common to use this term, but when we discuss the heat equation, it makes more sense to call this term numerical diffusivity. And you see it has also the right dimension. It has here velocity times length, that is length squared divided by time. In units would be meters squared per second. That is the same dimension and the same units as the thermal diffusivity has, and also as the kinematic viscosity has for that part. So if we think in that way, we can say the upwind method consists of a central discretization, and this, what is added here, or it's negative here, we can consider as a numerical dissipation. So that plays the same role as the thermal diffusivity term in the heat conduction equation. So it gives some smearing of the profile, some propagation of the profile. If we would have an amplitude, it would decrease the amplitude. And we can call that then, this part that is here, the numerical dissipation. That is then responsible for the diffusivity of this method, so that it makes discontinuities smeared, that it decreases amplitudes. That is due to this term. Okay, now we want to do an analysis of this method, the upwind method, in a little bit more detail than also we have done in the previous course, Introduction to CFD, last semester. And the technique that we are going to use is the modified equation. You have a very nice account of that in the textbook. And I'll show you how it works. So that is now the next point, that we look for the modified equation. And there we will see that we get even more information than just by this analysis that we did here, simply from the flux. So that is then what we look at, is called the modified equation. Of the explicit upwind finite volume method. And here we take it the 9, that was for the situation where U was positive. And that is the following. That is, we write it again in the form that we need. We have the time discretization, Tjn plus 1 minus Tjn divided by delta t, the time step size. And we have U positive, and then we take the difference to the left, Tjn minus Tj minus 1 from the side where the wind is coming from, divided by delta x is equal to 0. So that is the equation that we want to analyze. And we have here assumed that U is constant. That is all what we do for the linear advection equation. And for this form, we assume that it is positive. We have also assumed that we have an equidistant grid, where the grid spacings are equal, delta x. And we, for the analysis again, as we also do for the consistency analysis and also for the stability analysis, we look for, make the analysis for the equivalent finite difference method. For the because the finite volume method corresponds to the finite difference method in the interior. And if we assume we have periodic boundary conditions, for example, then they are exactly the same. So that means we do the analysis with the tools that we have for the finite difference method. So that is, we mentioned that here. So we regard then the finite volume method as a finite difference method to be able to do this analysis. And that means that we assume that our approximations to the cell averages in cell J at time table Tn are approximations to the values at the grid points, that is, to the exact values at the grid points. Xj at the time level Tn. So that is the background. So we use a finite difference analysis here. And now comes the catch. In the consistency analysis, we insert the exact solution of the linear advection equation into the difference method. In the modified equation approach, we do not do that. We insert a smooth solution that does not, which is not the exact solution of the PDE. Just a smooth solution that fulfills then the finite difference method. So that is the difference between consistency analysis and modified equation approach. That here we do not insert the exact solution, but a smooth solution. T, we call it the same as usual, T xt, of the finite difference method, not of the exact solution. So I want to stress that, the smooth solution of that, and that is then not the exact solution of the PDE. We insert that smooth solution into the finite difference method. So we imagine we have simply a smooth function and we put it into this equation. We assume now, to simplify the notation, that x is equal to the grid point xj and t is equal to the time level Tn. And from that, we have already used that yesterday when we looked at the consistency for exercise 2. It was the consistency of the forward time-centered space for the heat equation. That this corresponds then to the xj minus 1, and that the t plus delta t corresponds to the Tn plus 1. So then, when we do that, we get the following equation. We call it star. So we insert now here then t of x, and that would be then at the new time level. So with this notation, it makes then the next steps a little easier. We have x t plus delta t. So that is a smooth function just, minus the smooth function t at xt divided by delta t. So that is then when we put in the smooth function into here. Now we do it also here. That is, we get minus the constant velocity times, we have again t of xt minus t, and now we have here xj minus 1/2, which is then x minus delta x, and t.
Excuse me.
Yes?
Why minus?
That is wrong. It is, let's see. No, it's right. This is tj minus 1, and this is minus. Here is the plus, sorry. Here is it, you're right. This is plus, yeah, correct. That was wrong. So here it should be plus. That was a typo, thank you. The rest is okay. So that was plus and then divided by delta x. And that is then equal to 0. In the consistency analysis, this is not 0, but the truncation error. But here it is 0. Now we do Taylor expansion in the same way as we do for the consistency analysis, because we assume that this is a smooth function, that we can do that. So we do Taylor expansion around xt. And that is skipped below. So we don't write it. When we have any function, we assume, and also any derivative, we assume that it is at xt. So then we have the following. What do we need? We need a Taylor expansion here for time, and we need a Taylor expansion here for space. So that means we have t of xt plus delta t is equal to t at xt, which I skipped, plus delta t, the first time derivative, plus the delta t squared half, divided times the second time derivative, plus delta t to the power 3 divided by 6, the third time derivative, plus order delta t to the power 4. So that is the classical Taylor expansion up to 4th order. So we stop here. T of x minus delta x t is then, we do Taylor expansion again around xt. Now we have to do the derivatives with respect to x, and we get minus delta x tx plus delta x squared half txx minus delta x to the power 3 divided by 6t xx, and here we have also delta x to the power 4. So now we insert that into the equation star that we have obtained by inserting a smooth function t into that finite difference method. So, and if we do that, then we get the following. So first we insert that, what we have here, into star. Insert the Taylor expansions into equation star. And then we get on the left, we get t of x plus delta t. So we write all this here. T plus delta t time derivative plus delta t squared half times the second time derivative plus delta t to the power 3 divided by 6 third time derivative plus order delta t to the power 4 minus t. So that is this one here, divided by delta t. So now we get a problem here with space. Let's try it anyway. Squeeze it a little bit here. Minus u. And now we have here t minus that. T minus, and then we put in what we have here. All this stuff here. That is then t minus delta x tx plus delta x squared half, the second x derivative, minus delta x to the power 3 divided by 6, third x derivative, plus order delta x to the power 4, divided by delta x. And all this is equal to 0. So that is equal to 0. So that is now we see a lot cancels. That is the purpose of that. So the t and this t go. We can divide by delta t and reduce then the order here. Here the t and t, they cancel. We can divide by delta x and get here then order 3 in that case. So from this, all this, we get the following equation. So from this we get the equation, I call it with the number symbol. What is left? Time derivative, delta t half tt, delta t squared divided by 6 second, third time derivative. And then, let's see, have I again made an error here? It seems so. Same error as before. I think it should be, of course, a plus. The same error here. Please correct that. It should be a plus. Should be a plus u times. And then we have here minus minus gives us a plus tx. We have here minus delta x half txx. Minus minus gives us plus. So if we do that, we get the following. We get the time derivative of the temperature plus, so now I move the u delta tx over. And then we have the delta t half, second time derivative. And we have, let's see, I move also the xx over minus u delta x half txx. So I take it according to the derivatives here. First derivative, second derivatives, and now the third derivatives. First the time, delta t squared divided by 6. Third time derivative, and plus u delta x squared divided by 6 txx. And here I write the order terms, sign doesn't matter, to the right hand side. We have delta t to the power 3, and we have an order x to the delta x to the power 3. Okay, so that is now the equation that we are in fact solving when we solve the linear attraction equation with the Upland method. To get a better understanding of what is going on, we shall now eliminate the higher order time derivatives by this same equation to see better what the equation represents. So that is the task now. We eliminate the higher time derivatives by repeated application of this equation that we have just derived. Equation, I call it number, this number equation. And we do that now.
I'm sorry. Why is on the right side the order from time without minus?
The order means it's a constant times something that depends on delta x to the power 3. The sign doesn't matter. That is not interesting. That's the reason. Okay, so we want to derive then this, do this procedure and eliminate the higher order time derivatives to see what the equation represents. To do that, we need some space. Let's see. Try to, well, I do a little bit, to save a little bit of space, I move that down here. Order delta t to the power 3 plus order delta x to the power 3. So then I can write this in this form. So I just do it to get some space here. What we are going to do now is to make a table. And that is similar to what is done in the book on page 107 in the textbook by Fletcher, Tanhill and Anderson. And here we have first, we write the derivatives. So we write all the derivatives, and here we leave space for what we are doing. So here we have the time derivative. Here we have the space derivative. Here we have the second time derivative. We will also need a tx derivative, a txx derivative, a third time derivative, second time space derivative, txx derivative, and the txx derivative. So we look only now on the left-hand side. So the goal is to get rid of these terms here, this and this. We will see first, we will generate new terms. First we look at the coefficients of this equation number, this equation here. We look only on the left-hand side. The right-hand side contains the higher order terms. Coefficient for time derivative is 1. Coefficient for space derivative is u. Coefficient for second time derivative is delta t half. Tx, we don't have that. And txx, we have minus u delta x half. We have here we have delta t squared divided by 6. Here we have 0, 0, and here we have u delta x squared divided by 6. So how do we proceed now? We want to get rid of this term. So we multiply the whole equation by delta t half and derive it with respect to t. So we do the following. We do the operation minus delta t half, and then we do the time derivative on the equation with a number. So what do we get then? We get then here the second time derivative. So that will be the first. We get it with a minus delta t half. So we get it the minus delta t half here. Then we get minus delta t times u t tx. So we get the time derivative, and then we get then here minus u delta t half. So if we would go back to this, we would have minus delta t half times the time derivative. So we have considered this already, and we are now considering this. And that is the term that is then appearing here. U delta t half t tx. We have no x derivative from that. We have an x derivative from that. Let's see. No, we don't have. But we get a third time derivative, because when we have the delta t half here, we get a delta t squared over 4 times the third time derivative. So that means we get a term here, minus delta t squared divided by 4. Then we get a 0, and then we get from this here minus delta t half. We get plus u delta t delta x divided by 4 t xxt, or txx. So we get something here, and that is then the term, let us see, the term u delta t delta x divided by 4. And here we get the 0. So you see, we got rid now, when we add these terms, we got rid then of this here, when we add these coefficients, but here we added a new one. So we have to get rid of that. To get rid of that, we multiply our equation star by u half delta t and derive it with respect to x. So we do now this operation here, u delta t half times d dx of the equation star, the equation number. If we do that, we get x derivative of, and then with the right coefficient, so we get then this here, u delta t half, the sum will vanish, so that was the purpose. And now we get another second derivative, and that is then operating on u, so we get here a u squared. It's positive u squared delta t half times the second space derivative. So that was taken this into account. Now here, from that, we get a ttx derivative. And that is then appearing here. We don't get anything here, but we get something here, which is then u delta t squared divided by 4. And we don't get anything here, but we get a third space derivative by this here. We have to multiply that by u delta t half and derive it with respect to x. So we get a third x derivative here. And that is then minus, because it has already a minus u squared delta t delta x divided by 4. Okay, so far, and we will proceed in this way. Now we have to stop at some point here, and the catch is that we will proceed to get rid of these terms here, of all these time derivatives, and then when we sum up the coefficients, then we get the modified equation. And the result, let's see, we look at just at the result. I hope we have that here. I'm not sure whether I have it here. I think I do not. Well, here's the time, but it's right. No, I think I haven't included it here, but it is in the lecture notes, in the book. It's in the book, and then it turns out when we do this in the end that we get a coefficient that is related to the second derivatives, and we get a coefficient that is related to the third derivative. So in the end we will see we are not solving the linear advection equation, but we are solving an equation that has second and third space derivatives. And that means we are solving an equation that has viscous effects by the second derivatives, like the heat conduction, and that has third derivatives which lead to that the propagation of the waves is not correct. It's called a dispersion error. But we have to stop here and continue on that tomorrow.